All right, welcome everyone. Thanks for joining us today for Dry Scrubber Users Association, or DSUA, for the Dry Sorbent Injection webinar. I'm your current DSUA president, Jerry Hunt. For those of you who aren't familiar with DSUA, it's a nonprofit organization that's been around since 2008 with the whole objective of trying to foster collaboration and innovation for the dry scrubbing technology industry. Since 2008, DSUA has been holding annual conferences, but these webinars have been something that we've developed this year in response to COVID-19 to try and carry out that mission for at least for the remainder of this year until hopefully we can resume normal conferences next year. This year is a little bit different in that, historically we've done dry sorbent injection or DSI presentations in the past, but I'd say this year we've been trying to make an active effort to really integrate DSI into DSUA, as I believe there will be some overlapping, issues that we'll explore. Some new, but some overlapping, and then maybe there's potential for looking at integration of these various dry scrubbing technologies. So we think this will be an interesting addition and focus for DSUA going forward. As far as today's agenda, we've got Chad Donner. He's the dry sorbent injection subject matter expert for Duke Energy. So, Chad's got a lot of experience seeing a multitude of DSI systems, good and bad. So that'll be valuable. And he'll be giving a presentation. His first presentation will be more general in that it's about DSI system operational and practical considerations. And followed by that, he's going to give more of a site-specific presentation on Duke Energy's DSI system there and how it kind of evolved and why over time. So for those of you that are watching the webinar, feel free if you have questions. You'll see below there, you can click and submit your questions there through Slido, or if you think of them afterwards, you're always welcome to send an email to DSUA, and we'll try to get all the questions answered that during the session, but if we miss any, we'll try to follow up with something written. Before we get started, a couple really quick housekeeping items. So for everyone here, is like the previous webinars, we're going to record this one. We'll upload it. So for those of you viewing, if you have to hop off or someone that would be interested in seeing this, stay tuned for the link, and we'll be sure to share that. And appreciate you guys sharing it as well. I already mentioned again Q&A, how you guys can kind of send in questions, those that are viewing. But one new addition that's kind of a trial for this webinar is you'll notice below the live stream window, there's a tab for polls. So you'll be prompted a couple times throughout the webinar. A poll will kind of pop up, and looking to kind of get some live feedback from you guys on what you think about the presentation. So keep an eye on that, and please notice that. We appreciate the feedback. One big thing to make note, you guys have probably seen the emails from me, but we're getting near the end of the year, which means DSUA, we're going to have to elect some new board members. So stay tuned. We've kind of compiled the nominations and expect to see for the members last year and the few new members who've signed up this year. You guys will be receiving emails asking for you guys to put in your vote for who should join DSUA. We've got 4 open slots, so please participate, and keep on the lookout for those emails asking for you guys to provide input on who should be elected to next year's board to fill those roles. Last couple housekeeping items. Anyone that finds this content interesting and is looking for more, you can get a membership, or if you have a membership, you can get access to the DSUA archives through the website. We've got over 300 presentations, all dating back to 2008. So SDA, CDS, some DSI. Feel free to, if you have questions and you want to look into it, but there's more content there for you guys. And if anyone, is kind of a call for content. So we're still planning to do some more webinars before the end of the year. So if you've got interest in wanting to give a presentation, specifically, we're planning to do technology neutral, any dry scrubbing technology. You've got something about performance optimization, or we're going to do one about consumables. So whether want to talk about filter bags, nozzles, atomizers, lime, anything that would fall under consumables, you think that would be beneficial. So reach out to us, send us an abstract through the website. We are looking for folks to kind of fill those slots for the future webinars. And still evaluating. If you think there's going to be value and you have interest, there's a Dry Scrubber 101 we're interested in kind of putting that together if there's interest, as well as if there's any specific dry scrubbing related vendors to give technical presentations. We're also want to hear your feedback on that. We're happy to kind of assemble that as well. So before we get started, I will appropriately share my screen this time, and we would definitely like to acknowledge our sponsors. Again, a big shout out to these guys. A majority of these guys have supported DSUA year over year, but this year is extra special, seeing how we don't have a conference. So again, we appreciate the support. So we want to recognize them and say thank you. So for your guys' sake, this is this first sponsor. This is Reaction Analytics Solutions. So Dr. Guisu Liu is someone that specializes in providing engineering solutions through CFD modeling. He's got over 20 years working on both fuel combustion as well as CFD models relating to emission control technologies. And as a result, he's developed over 100 CFD models that have, result in some kind of engineering solution. So whether it's front-end combustion or back-end emission controls, reaction analytic solutions, they've got the CFD experience, as well as a unique trait that they also incorporate chemistry models. So it's not just specifically flow modeling, but they can incorporate chemistry modeling. So that can be utilized to optimize both the chemical and sorbent utilization. So and specifically to this webinar, the CFD has been something that we've seen utilized in DSI to help kind of fine tune the DSI solution. So yeah, again, thank you to Guisu, and you'll probably hear a little bit more about CFD modeling in Chad's presentation. Primex is they've been a kind of a mainstay here with dry scrubber users. Stuart Nicholson was one of the founders of DSUA back in 2008, so Primex has been involved in the dry scrubbing industry, for quite some time, providing comprehensive programs to help all, dry scrubber users optimize their performance and troubleshoot issues. So they've got a unique combination of not only dry scrubber knowledge about the technology and operations, but as well as patience to just kind of work through, custom solutions for folks, and their track record's evident. And you can see some of their clients here that they've had 20 years of success providing these services. So if anyone's looking for any kind of dry scrubber performance optimization, feel free to follow up with the folks at Primex. And last for this session, before we move on, we've got Lhoist North America, a subsidiary of the Lhoist Group, which is a global limestone, quicklime, hydrated lime, silicate minerals company. They've been a supplier of high quality products, calcium-based products, including the high pore volume Sorbical SP, SPS enhanced hydrated lime. That's been used for acid gas emission control at both power plants as well as a multitude of industrial applications. So in addition to that, Lhoist has a highly technical flue gas treatment team that's got several decades of air pollution control experience that can support custom solutions, whether it's compliance optimization or just simply troubleshooting a dry scrubbing application. Lhoist can be here to support that. So we will now kind of get started, but I want to turn over and recognize our moderator for today's session, Kurt Bean. Hey, Kurt, thank you for being the moderator for today's webinar. Kurt, quick background on Kurt. He's the technical director for Mississippi Lime, who's headquartered in St. Louis. In addition, Kurt is also one of the DSUA board members, and certainly he's been one of the folks instrumental to kind of helping get all this pulled together this year. I know being a board member this year, we've all taken on some responsibilities we weren't expecting, so everyone's had to kind of step up a little bit extra, which is appreciated. Kurt's been with Mississippi Lime since 2008, all focused on air pollution control, specifically around DSI as well as other dry scrubbing technologies. He's got his BS in chemistry from Southern Illinois University at Edwardsville, and his MS in organic chemistry from The Ohio State University. I remember the. So Kurt's prior life, he worked in the specialty chemistry industry, providing technical services in operations, quality management, and application development. So, and he also serves as a board of directors for the Worldwide Pollution Control Association, and he's got, had over a decade of planning experience working and coordinating the dry hydrate users group, which was specifically geared towards dry sorbent injection. You guys have probably come across Kurt as he's presented at numerous utility and industrial air pollution control conferences. And he was recognized in 2019 by Reinhold and received the Reinhold Environmental Roundtable Lifetime Achievement Award. So congrats on that, Kurt. And I'll shut up now and turn over to you. And thank you again for being our moderator.
All right. Thank you, Jerry. It's my pleasure to introduce Chad Donner. As Jerry said, he's the sorbent injection subject matter expert for Duke Energy. Chad's a graduate of the University of Cincinnati, and he's spent 15 years with Duke Energy, almost wholly in environmental compliance projects and acid gas control. While he's principally concerned with SO3 mitigation systems, Chad also has experience with HCl and SO2 mitigation using hydrate DSI. I've known Chad for probably over 8 years, and he has put considerable energy into understanding and implementing reliable and high-performing DSI systems for hydrated lime, and that's what he's going to talk about today. And he also has the data to back up those recommendations, and you'll see that in today's presentations. Chad works hard at optimizing chemical usage to extract as much value from the station as possible through unit flexibility and dispatch cost. And his focus is on enabling coal plants from yesterday to compete in today's economic and environmental climate. In addition to the subject matter expert work for Duke Energy, Chad is also a VP for the Worldwide Pollution Control Association, where he is also on the Utility Advisory Committee, principally working with condensable air products and byproducts committee. And in 2019, he was awarded a coveted members-only jacket by the Dry Hydrate Users Group for his contributions forwarding the knowledge of hydrated lime dry sorbent injections. So with that said, as Jerry said, Chad will talk a little bit about DSI, some general operational and practical considerations, and then talk about the evolution of Crystal River's DSI system design. So Chad, thank you for agreeing to present, and welcome to the Dry Scrubber Users Association, and the floor is yours.
All right, well, thanks for that, Kurt. Get my screen pulled up here and we'll get started. All right, so again, my name's Chad Donner, Sorbent Injection SME for Duke Energy, and I'm going to talk a little bit about just system design optimization, mainly focused on conveying air quality, and reliability factors. So just as a brief introduction, I'm gonna give you some background to dry sorbent injection at Duke Energy, and kind of our strategic approach, and then a brief introduction on SO3 formation and hydrated lime chemistry, as to why it's critical to employ some controls to convey it reliably. So Duke Energy's had significant experience with sorbent injection since the late 90s, and at that time there wasn't really a dry sorbent injection OEM kind of following. It was pretty much a relatively new technology back then, and I have historically broken down the industry into like a 3-generation phase, where the first generation is there wasn't a lot of involvement from vendors. A lot of it was utilities, trying to solve their own problems, and kind of cobbling together equipment, material handling equipment to solve this need. Second generation, some of your material handling and kind of ash conveying system vendors started getting involved, and approached the problem from a material handling standpoint and not much of a chemistry standpoint. And because of that, there was a lot of reliability issues with those systems, because you're handling a chemical that's reacting in the lines, and also throughout the entire system, there are chemical reactions happening. So where we're at now, what I like to call is third generation, where we understand some of those issues of the second generation systems, have enabled controls to address that. And I believe now we have the capability to operate with high performance and reliability. And again, the whole DSI process, it's a dilute conveying process. So you've got a lot of interaction with air, but I like to apply 3 T's: time, temperature, and turbulence to the process, where time is reaction time that you're spent reacting with air and other chemicals. Temperature is a catalyst for um, chemical reactions to happen, and then also turbulence, as in mixing and distribution within the ductwork and within the conveying system. So at Duke, we have taken like a programmatic approach to DSI application. We've got a mixed bag, anything from first, second, and third generation systems. And then, honestly, the squeaky wheel gets the attention on different upgrades and, issues that need to be addressed with their specific system. And one of the biggest takeaways are in past thoughts of DSI systems was you just had to get it in the duct, and I think at this point we're so much beyond that, where we have to provide this as an engineered solution and design performance and reliability in from the get-go, in order to make these systems effective. So many people that have heard me talk have probably heard me say everything affects SO3 and SO3 affects everything. So basically that holds true from the coal pile to the stack. So your boiler and SCR basically oxidize your SO2 that comes from the coal, that creates the SO3. O2 percentage plays a role in that. SCR MOT is dependent on SO3. NOx removal can also be affected by your SO3. Air heater pluggage and ABS pluggage, it has SO3 as a role. Heat rate is dependent on SO3. HCl capture and removal with hydrated lime has an impact with SO3. Mercury capture is dependent on SO3. Precips operate off SO3. And then the emission of blue plume out the stack, SO3 has a role in FGD as well. So quantifying all the benefits for heat rate, when you look at all of the constituents between material handling of coal, ash, landfill, credits, etc., there can be significant benefits to improving heat rate by taking SO3 out and operating the back end or the cold end of your plant at lower temperatures. And again, sorbent injection systems, I think, need to be thought of as an integrated control technology, and not just a standalone environmental control system, because they can affect the entire plant both positively or negatively depending on the controls in place. So taking the siloed versus holistic challenge at heart, and trying to apply a holistic look at it. And I would say in the past, dry sorbent injection systems have fallen short on means of control and long-term reliability. And again, as plants begin to rely on these systems to achieve these benefits to compete in the changing market, the reliability needs to be there to back those systems up. And again, third generation systems, I believe we have the ability to do that. So just a brief background on SO3 generation. Anywhere from 1 to 2% of SO3 can be created in the furnace, and that's depending on O2 in the gas and slag formation, which can act as a catalyst to oxidize the SO2. Another anywhere from a half to 2% can be oxidized in the SCR. So you can have anywhere from 50 to 100 ppm of SO3 entering the SCR, the air heater, at any time, and depending on catalyst life and ammonia slip levels, that can lead to air heater pluggage. And then continuing on from there, you're pretty much all vapor phase sulfuric acid at that point, which is then rapidly condensed in FGD, which causes your blue plume that SO3 is famously known for. So that was a little bit about SO3. Now, to discuss hydrated lime a little bit, at some point, this graphic really stuck with me, showing the cycle that limestone goes through. So I call it the vicious cycle of limestone, and basically all chemical products, I think, have a natural stable state that they want to be in, and that being calcium carbonate for limestone, obviously, and then it's calcined to create calcium oxide, and then reacted with the appropriate amount of water to create hydrated lime or calcium hydroxide. But at the same time, new reactions with CO2 can recarbonate that lime back into calcium carbonate, which can cause scaling and material handling issues in a dilute phase hydrated lime injection system. So being able to control those reactions with CO2, which are dependent on temperature and relative humidity, are where a lot of the effort needs to be focused in order to create a reliable system. An example of some of the typical reactions with acid gases and hydrated lime are shown here. It'll react with SO3 and or H2SO4. Hydrated lime can be used for HCl capture as well as SO2. I don't have an equation up there for that, but we do have experience using hydrated lime for SO2 capture in dilute phase dry sorbent injection systems. So getting into some of these system design and optimization factors. First, I'm going to talk about conveying air quality. Again, this is that calcium carbonate scaling that is formed if you don't have proper conveying air quality control through drying the air out. Again, it's a function of the relative humidity and the temperature of the conveying air. A lot of the second generation systems used a desiccant dryer only, which desiccant dryer doesn't do a great job at removing moisture alone. So it needs to be, the air needs to be brought to saturation in order for the desiccant dryer to operate effectively. And then, carbonation, obviously, if you're converting your hydrated lime to this calcium carbonate, it reduces the effectiveness of it in the flue gas, which is what the end goal is here. And then, pre-chilling the air is the most effective way to, coupled with a desiccant dryer, are the most effective way to control the conveying air quality. So I've kind of compared the different drying technologies. So full conditioning is what I consider pre-chilling the air and coupled with a desiccant dryer. Partial conditioning is desiccant dryer only, and then also compared that to no conditioning at all. So on full conditioning, we get down to you know, low single digits of dew point, and then on the grains of moisture, 20 grains of moisture per pound of air. And then if you look at the dew points and moisture for partial conditioning, they are not significantly lower than no conditioning at all, because when the air is not at saturation, the desiccant wheel is not very effective at removing that moisture. So from a dew point standpoint, uh, you're looking at, you're still looking at like a 60-degree dew point with partial conditioning versus a 70-degree dew point, with no conditioning at all. Through some of we've got 3 different, I'll say, 3rd generation systems. And with those, we had some design changes of our moisture set point between them. Our first system had great reliability. The second system, we started noticing some initial reliability problems that were new to me, with rotary airlock squealing and some pluggage. And what we found out during that time, the design set point for moisture changed from 5 grains of moisture up to 30 grains, because there's concerns in the industry about having the air too dry. But I think through our experience here, we pretty much debunked that myth that 5 grains was too dry, and actually 30 was on the point of being too wet, and we were having partial calcium carbonate scaling. A couple years ago, I found a report that was done that basically showed that below 8% relative humidity, the ability for calcium carbonate to form basically ceased to exist. So I basically plotted that. This is a curve showing, the 8% relative humidity and the conversion factor on the x-axis. So it, basically up at 100% relative humidity, you'll convert roughly 35% of the hydrated lime to calcium carbonate. And again, below that 8%, there's a 0% conversion. So I compared the different systems that we have on a grains of moisture and relative humidity, and basically it showed that the system where we changed the set point from 5 to 30 grains of moisture was above that 8% relative humidity point, and the relative level of pluggage and scaling that we saw made sense based on the scaling that we were seeing. So I plotted these results on a psychrometric chart, and Cayuga was the 5 grain point, and I've shaded the area in green below 8% relative humidity. And then Blues Creek was the one, the site that was the 30 grains, and you can see it's just slightly above the 8% curve. And the pluggage wasn't bad, but it was just enough to be annoying. And again, that's relatively speaking the amount of pluggage that we saw. And then you'll see the Roxborough Mayo pin up there. They have no air controls at all. And that was the site that had, if you remember a couple slides back, the pallet of elbows. So their solution to scaling and pluggage was to just recycle and clean elbows as they plugged up. They would run, less than 2 weeks before they had to swap out elbows. So we were able to modify the settings on the dryer for Ballew's Creek and brought that down to within the safe green zone, below 8% relative humidity, and moisture scaling pluggage issues haven't been an issue there. And East Bend, which is a new system that we currently started up, it was also modified to be within the 8% relative humidity, and it's been running for since February with no pluggage or scaling to date. This is an example of a DCS screenshot from the Cayuga station. You can see the dew point is running at 12 degrees Fahrenheit, and the ambient temperature is roughly 48 degrees. So this is all the same day. Just for comparison's sake, I went to weather.com and got the outside ambient air conditions. The outside conditions were basically saturated with a high dew point. And you could, if you remember from the DCS screenshot, the measured dew point in the conveying air was 12 degrees Fahrenheit. And so the picture on the left is what the sky looked like outside. And the picture on the right is the condensate drain off of the dryer. So that's the amount. I mean, we're basically pouring a continuous stream of moisture out of the conveying air that would have been conveyed with the hydrated lime, causing scaling and pluggage potential had we not had the drying system installed.
Hey, Chad.
Yep.
We have a question from the audience, and they want to know, are you typically measuring the moisture in the conveying air? And if so, how?
Yes. So we have a dew point in situ dew point monitoring probe that can measure either dew point or relative humidity, depending on how it's configured. And that is installed after an aftercooler. So we have a dryer, blower, aftercooler. Then we have the moisture. It's a combined temperature and moisture monitoring device. So that was conveying air quality. I'm going to move on to different reliability factors. Probably one of the most reliability sensitive parts inside the silo system is actually the expansion joint between the weigh bin and your rotary feeder. So in the past, it's been like a really flexible rubber belt, basically, that's secured with hose clamps. And those would always blow out and cause, the silo to fill with hydrated lime, and it's really a safety hazard. So finally, I found a good expansion joint that we retrofitted the last project with that is actually rated for load cell application. So it doesn't transfer any load to your load cells that could disrupt your feed rate calculation. So that was a good find, and so far those have been operating very reliably. And you can see all the hydrated lime residue here was from leaks from the previous joints that we eliminated and took care of with this design. Here, another safety aspect, we've got weigh bin vent filters inside the silo that originally exhausted in the silo. So we routed all of the vents to the outside. And then the picture on the right, you see pipes that transfer that down to grade, where you can basically feel and measure the rotary airlock blow by the relative amount of air coming out of the vents. That can be used to determine rotary airlock wear over time. And again, you want to keep the air in the system and not blowing past your rotary airlock, as that'll create feed issues. Elbows in the system. We like to use long radius elbows made from rubber hose. These are a system design that used a cast iron wear elbow because this vendor thought that hydrated lime was abrasive like ash and would eat through elbows, and that's just simply not the case. And also made it very challenging to change these elbows out in certain areas due to their weight. So a standard that we use on our new systems is a urethane kind of gum rubber lined hose it's an abrasion resistant liner. I've had these hoses in service since 2015 with no wear through. And again, 8 times the diameter is typically the hose radius that we like to use to minimize turbulence and mixing in those areas to try and maintain smooth and even flow. Same for the small bore hoses that go to your lances. Typically, these are anywhere from 1.5 to 2 inches. Anywhere you have a constriction in the line cross-sectional area, a lot of times you'll form scale in those areas. So we found a hose fitting that expands from the inside out to maintain the same flow area through the fitting, so you don't have that constriction and possible scale formation site. So all of our smaller bore hoses, we use these internal expansion stems. And then the large bore piping, like 4-inch, 4, 6-inch, we use clamp-on flanges that are easily taken apart and serviced for maintenance if needed. Again, on the small bore hosing, usually from our splitter to our lances, everything is equal length hose 100% of the way. And we use cable tray to control that and try and keep it in a smooth conveying path to eliminate tight bends in areas that could be prone to wear if you had a tight bend, and maintain a smooth flow path. Again, another example of, basically the hose routing and maintaining smooth bends being critical. You want to try and have the pressure balanced as much as possible from lance to lance, so that they all have equal opportunity to get the same amount of flow. And results are basically here. I mean, I haven't updated these in a while, but the results are pretty typical here, and many people that are familiar with dry sorbent injection systems of the past would realize that these pressure profiles would normally look like a sawtooth graph, where things would gradually plug. You'd have to shut the system down, clean, and then you'd gradually plug until you had to shut it down and clean again. We've maintained this. This is showing, I believe, almost a 2-year time period where there is no, gradual increase in pressure to the point that the system had to be shut down, with exception of one spike where the condensate drain on our dryer got plugged, and we carried over moisture into the conveying system. And outside of that, that was the only pluggage event that happened on that system. And again, the new system that was installed at East Bend, like I said, we started that up in February, and it's been running consistently since then without any pluggage to date. And that is the first presentation.
Hey Chad, this is Jerry. Really, really great stuff in there. And from my perspective as a Lime guy, it's still, I think this is great. I know you guys have gone through this stuff and learned a lot, which is great that you share it, because I still see a lot of these are common issues people are still encountering today. One question I had that seems to be, I always have this question at a plant and I very rarely get a good answer on it. So I'm interested if you got something to share. Obviously the desiccant wheel dryers are an integral piece to controlling the relative humidity. Do you have any recommendations or advice for people with those on how they can monitor and tell that they're doing what they need to do or that they need to be serviced, or any kind of indicator? Because as you kind of noted, if they're not operated properly, they can cause more harm than good.
Yep. Yeah, I mean, I think that's where having your dew point and relative humidity monitoring in the system is critical. So if you've got an upset with that dryer, you're going to see a either a step change in that or gradual increase over time. So trying to maintain, and that's obviously trainable on a Pi data system or whatever your data logger is. So I think having that dew point indication in your conveying system is critical just for system health overall. And you can correlate that to, pluggage events that you may have, where you may have issues or not have issues.
Hey, Chad, what can you speak to some key safety considerations for operating a hydrate DSI system? Where are the risk points, and what things does Duke do to sort of mitigate those or manage those risks?
So I think the big risk points, obviously, your number one risk in a hydrated lime system is maintenance. So if you can eliminate the amount of maintenance you have to do through reliable operation, that's less risk you're putting your maintenance and operations folks um, on that system. So another issue or area that we focus on, obviously the silos are all prefabricated and they're sized to ship on the road, so they're limited in their overall outside dimension or their diameter. So those areas are usually pretty cramped, and there's a lot of hydrated lime potential in those cramped quarters. So trying to take as much risk out of the silo skirt as possible by piping vents outside, looking at those expansion joints to improve the reliability of those and minimize leak potentials inside the silo skirt is a big one. Other than that, dropped object prevention is big for us. A lot of times you've got elbows that are up in the air. We've got access to all the elbows should we need to do maintenance. And then we've got permanent dropped object prevention measures on all of our handrails to, protect workers below during any maintenance activities on these systems. But again, I think the biggest, addressing the risk is improving the reliability so that you're not constantly having to maintain these systems.
Okay, thanks. And then what on your silos, what level transmitters have you found to be most reliable? Because you're dealing with, I guess during unloading, you're dealing with a very kind of a loose bulk density,
Yep.
and then when it's in operation, it's probably more of a packed operation.
So we use a Siemens radar level transmitter that has a air purge on the lens to keep any dusting off of it, and we see very good trending with it over time. You will see directly after you unload a truck, you'll see kind of a high point, but then it settles down within minutes. And then it kind of falls right in line with where the trend would have been. So if anybody wants or needs any information on those, I can send that out.
Okay. To follow up on that, Chad, to add to that is, do you guys suggest just a single level transmitter, or have you seen any benefit with multiple level transmitters? Just thinking, an experience of, say, a rat holing occurs
Yep.
and getting false readings. What are your suggestions
Yeah,
there?
so we do use redundant transmitters just to kind of check one against the other. You know, if one is kind of trending away from the other, if they're both tracking together, then you can feel pretty confident in your level indication.
Okay, we got a question from Kevin Redinger, and this is an interesting one. I want to hear the response because it almost kind of charts the history of DSI. Can you comment more on where injection lances are located in the overall layout of the air quality control system?
Yeah, so I probably should have mentioned that on the overall view of the SO3 generation slide. But you know, in the past, everything kind of started out as close to FGD because the primary concerns were SO3 and blue plume. But slowly, the industry caught on that there's more benefits to taking SO3 out on the performance of other air quality control systems or plant equipments. So it moved from post ESP to pre SP to pre air heater, and then now we're even doing injection pre SCR. And there's different benefits to each one of those locations. Your SCR is dependent, your SCR minimum operating temperature is dependent on SO3. So as solar and wind and other more critical, it's more critical to get the coal units to turn down more. And at the same time, our NOx limits are still they're more stringent and becoming more stringent that we have to keep the SCRs in service. So in order to achieve both of those goals, we have to get the SO3 out before the SCR. And again, that's primarily a low concern. Then you've got air heater pluggage, which benefits from pre-air heater injection. So I guess in summary, it kind of makes sense to inject as far up in the stream as possible to maximize your secondary benefits.
Thanks, Chad. That was, I know that could be a presentation all in itself to answer that question. So that was the abbreviated version. So one thing that I think I'd be interested in your perspective. Again, you guys have a whole fleet of DSI systems. You've kind of shown that some have the, say, full conditioning, some have no conditioning. What would you say has been the challenges? Because clearly you guys have got data at some of your installations to show that the correlation between a proper conveying air design and reliability. But you know, what challenges do you expect or have you seen to try and justify the retrofitting your other systems to kind of do that, and as opposed to, you know, having a pallet full of elbows?
Money and capacity factor. So you know, capital to make the improvements and then being able to justify that long term with expected capacity factors of the units. So we've had to get creative in a few different instances where, you know, I'm starting to look at changes in dispatch and correlating that to dollar values to help justify improvements. But it's still a challenge to get capital approved for coal plants with lower reducing capacity factors.
And I assume the economics to that would be the plant would have to have some kind of data to show that this is how much O&M time they're spending in addressing reliability issues and doing some calculation on return on investment to spending the capital. I assume that that's kind of what's required to justify that, right?
Yep.
Yeah. Okay. Yeah. You just see that a lot. And, you know, I recognize it's probably hard to justify those operating costs because they're not necessarily easy to track if people aren't always tracking them. So, we got time for maybe one last quick question. And you put up one of your last slides. You talked about equal length hose to kind of balance the flows and whatnot. I'm guessing that maybe you guys have had an experience, a bad experience to help you kind of learn that. You know, it's just not good engineering principles, which it is, but I feel like that's one of those things you learn from a bad experience, and it kind of sinks
that in the next presentation.
Gotcha. Okay. All right. Well, we could ask a billion questions, but I'll be quiet so we can, Kurt, you can take over and we can transition over to the next one.
Well, Chad, I think you're gonna talk more about a specific unit and kind of the evolution of Crystal River and their DSI system, which I think was what generation to the other. You took it from what, generation 1 or 2?
Yeah, it went from generation 1 to generation 2.
Okay.
And generation 2 didn't work as well as generation 1, which has been pretty much the typical in the industry. And dryers drying the air actually got a bad reputation because of that.
Okay.
All right, so let me pull up that one, and we'll.
Jerry, do you want to?
Yeah. Real quick.
Interlude.
Good. Yeah. Good housekeeping. Real quick. Again, I think it's super important to recognize our sponsors and kind of breaking it up before we get started. And again, a big thank you to these guys because you know we probably couldn't be doing this year as well as next year if it wasn't for these folks. So important to recognize them. You know, Mississippi Lime, again, they've been a sponsor this year throughout and got over 100 years as a world-class producer of calcium-based products. Again, quick lime, hydrated lime, limestone, and it all comes from one of the richest limestone reserves in the world. They've got over 12 plants and terminals to be able to give you a multitude of product supply all throughout North America. You know, again, both ranging from high quality quick lime or multitude of hydrated lime products that can be used to develop a cost-effective solution for various dry scrubbing applications. So your moderator here, Kurt, you know, if you guys have any questions on hydrated lime and want to reach out to Mississippi Lime, he's your guy. National Filter Media, again, also one of our sponsors. You know, they've been around since 1906, so they're one of the oldest and longest term provider of, you know, filtration products for air pollution control. They kind of pride themselves in the fact that while the industry's changed a lot since 1906, they still have the same fundamental focuses about developing partnerships and earning trust of their customers through not only the quality of their products, but as well as their customer support. So, you know, if you guys got bag related questions as it correlates to your dry scrubbing needs, and you know, Keith here at NFM will be a guy for you to reach out to have a more conversation with. And Gecko Robotics, for those who were on the first webinar, you know, Dave Kahn from Gecko was our moderator, and you know, Dave's been also instrumental in working with DSUA over the years, previously a board member. And Gecko, they utilize a revolutionary wall climbing robotic technology, so enables you to do inspections of various infrastructures, for example, the internals of, say, a silo or a scrubber or a boiler. Between the robots and their inspection team, they've been using this technology to perform these NDT inspections throughout the globe. So it enables the end users to be able to perform these routine inspections with this new technology in these hazardous environments, both quickly and more importantly, safely. So, and at the same time, they're able to generate reams of data as a result of that. So again, a big thank you. These are all of our sponsors for the DSI webinar, and can't say enough thanks for them for all their support throughout the year. So beyond the folks that, you know, we referenced on our slides, Carton, Fujikin, Graymont, and RPM Solutions in US Lime also. So if you guys want to learn anything more about any of the sponsors, if you scroll down for those viewing the live streaming, you can click on some of their websites and get more information, or simply just come to the Dry Scrubber users website or email us, and you can get a direct link going to their website there. So that's all I have, and last time I will interrupt with anything commercial related, and I'll turn it back over to you guys, and thank you for letting me interrupt.
All right. Well, Jerry actually gave me the idea for this next presentation, and get pulled up here. basically talking about the evolution of the system that we have at our Crystal River station. And I'm really happy with how this presentation turned out. So this is the first time I'm giving it, but I'm pretty excited about it. So our Crystal River site, one I'm gonna go into kind of some background on what their issue was here, but basically they're our only fleet site in the fleet that has an SO3 limit. So there's some added scrutiny around that kind of drove a lot of this. So I'm going to talk about some evolution that happened at the site, from induct distribution improvements to reliability improvements, and then lastly, lance to lance distribution improvements. So they have a sulfuric acid mist compliance assurance monitoring limit. And kind of how that came about was the SCRs and wet FGDs installed at Crystal River were put on late in the game in the 09 to 10 time frame. And with the addition of those unit or air pollution control devices, a sulfuric acid mist limit was in effect from day one of that equipment being installed. So their SAM limit was 0.009 pounds per million BTU, which equates to about 2 to 3 ppm at the stack, and they complied on annual compliance tests. The original sulfuric acid mist mitigation technology that was installed was an ammonia-based system, which was very effective, but essentially made ash sales impossible. And on top of the safety concerns associated with a ammonia-based system, through dewatering systems, ash handling, all of which have ammonia present, and through excursions could have high levels of ammonia off-gassing. The CAM plan was based off of, or established, a load versus injection rate. So pretty simple. There wasn't any real consideration to changes in fuel SO2. It was purely a injection rate of SO3 mitigation chemical to load on the unit. And then shortly after operation, due to loss of ash sales, a CAM plan revision was initiated to include hydrated lime injection. The site quickly transitioned to a temporary injection system while a permanent system was being designed and installed. That led to a number of other issues. Again, there's several regulations that applied to the operation of these, they call it acid mist mitigation systems. So again, their original was ammonia, and then they, included the hydrated lime under that. But some of the rules for operating the system were any injection rate less than 100% of the control curve was considered an excursion. The injection rate was to be evaluated over a 1 hour average. So their hourly injection rate that had to comply with no less than 100% of the injection rate curve, which many of you that are familiar with dry sorbent injection systems, the injection rate likes to swing around a little bit based on, just the filling and emptying of the load cells and calculation of that injection rate. So that in itself is a challenge. Then excursions are allowed under the following circumstances only: startup and shutdown, during load ramps. But this last bullet is probably the most important: a malfunction of 72 hours or less per event and less than 480 hours per year. So anybody that has spent much time operating an older hydrated lime injection system knows that 72 hours is a challenge for a large plugged event, and then also 480 hours per year is not that much. So again, a temporary injection system was initially used to kind of transition away from ammonia, and a lot of the initial testing was done with this temporary system to validate and build that hydrated lime versus load curve. Once the permanent hydrated lime injection system was started up, it was actually noticed that the injection rate required with the permanent system was more than with the temporary system. So the sizing of the permanent system was based off of the data analysis and testing on the temporary system. So immediately we ran into a capacity issue with the permanent system that was basically taxing the maximum capacity of that system. And then again, reliability from day one was an issue with pluggage all throughout the system, elbows, lances, you name it, to the point that 72-hour limit and the overall hours on the year were being challenged. So again, given the capacity and reliability concerns, compliance with their SAM-CAM plan was in jeopardy. And that's when, the station engaged help from Central Services, myself, to start looking at what we could do with the system. I guess it's also important to note that, the transition between all of this happening of when the initial testing on the system was done to, building that permanent system, to starting to address the issues was all when we merged or merged with Progress Energy. So this is a legacy Progress plant. So a lot of the design work and testing was already in the works, and then so they didn't really have the benefit of a lot of the work that we had done in the past to being built into the system at the time. So first time I went there, we were able to do some ductwork walks, and I was able to just do a thorough evaluation of the entire system. Again, throughout the industry, I think it's starting to become widely known that straight tube lances don't give you any mixing. Basically, the hydrated lime basically streams directly downstream from them. The top right picture, you can see the orientation of the lances in this kind of smiley face arrangement leaves a large empty or untreated hole. Couple that with the lances being located directly upstream of turning vanes, which are going to negate any kind of mixing that you had. And they were chosen, that location. This is the ESP outlet location as a SO3 polishing step. The lower left picture, there is an opacity monitor that they were still complying on. So they put the lances directly downstream of the opacity monitor, which again put it directly in front of the turning vanes. So not an ideal location for getting good mixing in reaction with hydrated lime. Bottom right is the SCR outlet injection lances. I don't know who thought that would be a good idea, but all of the lance lengths are exactly the same in the center of the duct, all the way across the duct. Not a good way to get good distribution. And top left is there's a lot of hydrated lime laying on the floor where just lack of mixing and material layout. So distribution is critical to achieve good, consistent performance. Passive flue gas mixing, basically creating turbulence while still maintaining a simple lance design, is kind of been our approach. And getting the hydrated lime mixed quickly and react quickly will minimize the chance of the hydrated lime going after other constituents in the gas that are maybe less wanted. So in this case, actually, if you've got localized areas, a high molar ratio lime, it's going to go after all the SO3 locally and start to go after HCl and some other things that are going to reduce the effectiveness of your hydrated lime. So again, getting the lime mixed quickly and distributed quickly is the best way to combat that issue. Here's just a typical installation of the mixing lances that we use at Duke. They create localized turbulence to get the hydrated lime mixed up quicker in the flue gas. So after seeing that, we initiated a CFD model due to the complexity of the ductwork at Crystal River. A number of items made this modeling and the overall distribution a challenge. So it's kind of tough to tell in this wireframe model, but they had 2 exhaust flues that split into 3 different air heaters. 2 of the outboard air heaters wrapped around the ends, and then the center one dropped out of the bottom of the ductwork. And then all 3 air heaters exited into a common plenum, which then exited into 4 separate ESP inlet flues. So a lot of things happening here with a lot of turning vanes. Probably the most challenging CFD model and distribution challenge that I've had out of any site. So after doing the modeling, we did the modeling with intent of improving the distribution. We added the mixing lances. We also did a trial with high reactive hydrated lime. So as you can see from the table, the as-built configuration required about 3,200 pounds an hour of lime to meet their limit. Cobra lances alone, or the mixing lances, took us down to 2,400, or a 25% improvement. And then when we couple both of those with the high reactive lime, that gave us an additional 20% improvement for nearly a 50% reduction in hydrated lime usage for the same amount of SO3 removal, at a tune of roughly, $600,000 a year in savings. And just from so because Crystal River had an SO3 limit, there's a significant amount of SO3 data that was performed consistently at the same locations in the stack. So we had a large mass of SO3 data and felt very comfortable with the testing results. So the far left family of curves with the green, red, and dark blue are all of our baseline data with the original configuration. And then the purple line was data that was taken after the Cobra lances were installed. And then the light blue was the combination of Cobra lances and high reactive lime. So, based on that performance, the original SAM-CAM compliance curves were updated. Top left is the original curve, which at 700 megawatts took roughly 3,000 pounds an hour to meet the limit. And then bottom right, 700 megawatts, you're in the 2,250 range, 2,300 pound an hour range. And then there's 2 curves on that chart, one for standard hydrated lime and one for high reactivity lime, which then drops you down into the 1,750, 800 range. So that was the performance side, the initial performance push for Crystal River. And then kind of shortly after, we went into a reliability improvement. One, they installed desiccant dryers only. So again, they weren't very effective at removing moisture and did not get us down to that 8% target. Their aftercoolers basically were undersized and could not get us to our target temperatures of between 90 and 100 degrees. We added dew point indication here so that we could accurately monitor what was going on. We added a common chiller unit to the inlet of all of their blower or desiccant dryers. So that was kind of a creative way to, optimize capital cost for the unit. And the condensing units are generally pretty reliable. So we felt comfortable using a common unit. Coupled with that, the system had a significant and excessive amount of those heavy cast iron elbows. So the station kind of simplified the routing where it was feasible or where they were having a lot of elbow issues, and used this clear polyurethane hose where they could kind of watch the flow and look for issues. Also, the lances that we use, the original lances they have were not shielded. It's basically a pipe carrying hydrated lime stuck in a high temperature 700-degree duct. So by the time the hydrated lime gets to the bottom of that lance, it gets hot, it starts to scale. So everywhere else we've implemented these shielded lances that basically pull in ambient air around the pipe actually conveying the lime, which gives a cooling effect, which helps to prevent scaling and pluggage of those lances. So the lances that were used here implemented this type of technology to help keep the lance cool, keeping lance reliability up. So for a number of years, the site operated with that until kind of the last 2 years. Maintenance has started to slack off, and they started getting closer and closer to their limit again, and we're looking for some new ways to improve their margin. So we started looking at lance to lance distribution. So I kind of split it down into, or simplified into, series splitting and parallel splitting. So the system was originally designed with series splitting, where it relies on a common header with reducing pipe diameters to try and control the amount of flow to individual lances, where the hydrated lime enters through the center of that header and then gradually kind of necks down on either end. But in most cases, the majority of the lime exits the header through the first or second lance, leaving the outboard lances starved of hydrated lime. So in order to combat some of those issues, in the past, the station has installed these, it's basically just a pipe reduction or an orifice to try and balance those flows and push more lime out to the outboard lances. But it was commonly observed, prior to this happening, that the outboard lances didn't have any lime flow at all. So if you've got 4 lances per duct, 8 lances per unit location, you're effectively reducing the distribution in the ductwork by 25% if you have 1 lance out of service or not receiving lime. So that led to the most recent upgrade, where we transition to what we use on all of our new systems is what I call parallel splitting, where all the hydrated lime comes into one splitter, and then this splitter design relies on symmetry and equal length hoses and pressure drop to equally distribute all of the lime. So basically this splitter exposes all of your lances to the same amount of hydrated lime in one compact spot. So they all have a greater chance of achieving, a low standard deviation of hydrated lime being delivered to each individual lance. And again, retrofits aren't always the cleanest, but here we were able to creatively use the existing header to kind of help support and hold things and try and give us as clean and smooth of installation as possible. We would have liked to had the purge lances relocated, but again, we're kind of in the middle of, capital cost to complete the upgrade and, benefit extracted. So ideally, you'd like to have purge lances located at your splitter so that you could purge the whole hose and down through the lance. But here, the purge lances are still located directly at the lance. I believe that is it. Any questions on?
Thank you, Chad. I guess questions will filter in, but we do have one that came in right at the transition. Let's talk about SCRs. And the question is, are there any potential issues on SCR operation when injecting hydrated lime upstream of the SCR?
We've done it. We've done some kind of exhaustive research and studies, with different catalyst vendors to see if there would be a potential issue with the hydrated lime on the catalyst, but we haven't really come across any, and certainly haven't seen any negative effects. We've got a unit where we're injecting ahead of the SCR that is operating down to 520 degrees, which is anybody that operates an SCR knows that that's extremely low on a high sulfur unit. And we wouldn't be able to do that without the hydrated lime.
And that's been the general industry experience with pre-SCR injection as well. Is that your understanding?
Yep.
And then what kind of benefits? I mean, you're generally with enhanced hydrated lime, and I know the cost of some of it, but what are the performance aspects that you think are beneficial if you start pushing injection earlier in the process?
Well, I think the big one is obviously air heater pluggage benefits, and if your station can start to get comfortable with that, you can start to turn down your gas exit temperatures and capture a heat rate benefit, which at some sites can be fairly significant. I have one site that we are just now getting into optimization on. They preheat their combustion air roughly 100 degrees, which is a substantial amount of steam and heat rate impact. So I am excited to be able to reduce that down and basically show that heat rate improvement that we've got. We did some testing on it back in the 16 time frame, and it improved their heat rate by roughly 70 BTUs per kilowatt hour.
Chad, this is Jerry. Just a kind of a little bit of a outside of the box thought, and kind of spin off of that, ask your idea, kind of thinking cross-functionally across different scrubber technologies, is that, have you ever put much thought in, or what is your opinion on, say, someone that has a circulating dry scrubber that's using hydrated lime? And with DSI, obviously, we're flexible about where we can inject and modifying it, but taking advantage, if it's a high sulfur application with SO3 present, now they're injecting lime into a CDS, but what about the thoughts of utilizing that technology to somehow take a slipstream of the fresh lime feed to help control, say, SO3 further upstream? Is that something that you've ever heard of, or what's your general thoughts on that?
I haven't heard of it, but it'd be interesting to see. I mean, I'm sure there's still some residual reactivity there that could be used. My only concern would be, I'm sure there would be new material handling challenges there, conveying that material with different chemistry than what we currently know how to, or have kind of, I'm not going to say perfected, but have been able to convey reliably. I'm sure any
Even
sulfur
just
amounts in there would
even just an offshoot of the fresh lime feed somehow.
yeah, okay, yeah, I mean, think that would, I mean, we've got a site that's got a spray dry absorber. It's located after the air heater that occasionally still suffers from air heater pluggage. So they could, potentially benefit from some sort of DSI ahead of their air heater and or SCR, depending on their load constraints.
Well, I think it ties to kind of what you said in the last presentation about it being like an integrated solution,
Yep.
just lime injection in general. So it's, I think, an interesting concept to consider the way coal plants are swinging low these days.
Chad, we have a question from the audience. What high-graded lime properties do you monitor or track for quality control?
I don't. I trust you guys.
And that's the key answer there. Hey, so like as far as actively tracking,
yeah, I mean, I think if you can get the material out of your truck, then we can convey it. That's kind of been our thing. So the one thing that we do that I didn't mention earlier was we provide dried air for offloading trucks so that we don't accumulate any of that ambient moisture through offloading the truck into our silo, which then has a trickle down effect on feeding the material out of the silo. So if we offload the truck with dry air, we're not putting that moisture in our silo that can impact, feeding material out of the silo.
Okay. Have you experienced any sorbent settling on the duct bottom, especially at low load? Any advice that you can share on that?
So yes, we've got some issues with that, but in general, the only sites that we have that issue are hot side precips, where we are injecting after the hot side on the low dust side of the duct. And, they have dropped their minimum loads further. So one, that ductwort's not designed to sustain fly ash. So we do see layout there. But any sites where we're injecting where fly ash is present, or anywhere you're injecting upstream of a precip, if it'll convey fly ash, it'll convey hydrated lime.
Okay. Another one, when you tested DSI injection upstream of the air preheater with the resulting heat rate improvement, did you also perform any air heater upgrades as part of that?
We have not yet. I've got one site that has been looking at that, where they are looking to make a basket design change. Their gas outlet temperatures at times reach 350, 370 degrees. So there's a lot of margin to be gained at that site. So that's one thing that we're looking at.
Okay. Jerry, do you have a question?
You know me, I'm full of questions. So
it's 10:23, so I guess audience, if you've got questions, we can probably take a couple more if you get them typed in quickly. If not, we'll probably do one more.
Yeah, it sounds good. I got one for Chad. I think I know that some people have different levels of understanding about sorbent dispersion, and it's clear from the work you guys have done that you guys have seen the value of a good injection grid and a bad one. I'd be interested to hear from your guys' perspective, just because what you've learned in that process, because I think there's a perception, you come across some sites where they may stick one or two lances in, and I think the perception is it just balloons up. And so I think for some folks who necessarily haven't had a chance to look at duct cameras or see what you've seen, what could you share? What kind of advice would you give to folks in that consideration from sorbent dispersion?
Yeah, so the big thing, what I've heard comments from the industry in the past is that, you just need the residence time. You need the residence time. Well, it's not as dependent on residence time as it is getting the hydrated lime distributed quickly, because residence time, if you're not getting the material distributed, the coating, the outer surface of the hydrated lime will be reacted with other chemicals, CO2, SO2, things that you're maybe not necessarily targeting, and it's going to be ineffective for what you're actually trying to do. So that's where getting it mixed quickly with all of the flue gas is critical to get the the high level performance that you're looking at.
Okay, and we've got one audience question, and I may piggyback one of my questions. I may add to it. The question is, any advice to prevent bridging in the silo? And then when you get into that answer, also, you want to prevent bridging, but also what do you do to sort of soup up the outlet to where you've got a consistent flow of hydrate into the stream, where you don't have like this sort of slug or this pulse flow?
Okay, so bridging in the silo, I think a big piece to that is drying the offloading air. If you get truckloads when it's a foggy day out or it's raining, just imagine how much moisture you're putting into the silo. That's going to cause the lime to have more possibility to cake and kind of compact and bridge over. I know I've seen instances where a truck is using their blower and it's a foggy day, and you can just watch the fog cloud go into their blower inlet. So I really think there's a benefit to having dried unloading air. The other piece of that question, where slug feeding into the conveying line, is kind of what I think you're saying, Kurt. All of our new systems, we don't use a rotary airlock for our feeder. We use a screw conveyor. So we've got a lot of turn down. It's, you can smoothly control the flow from, 20 to 1 turn down. So I think it goes to like 10 hertz or something like that, all the way to full speed.
Okay. All right. With that, it's 10:27. Chad, thank you very much. We appreciate your expertise and sharing this information. We appreciate Duke for allowing you to share it. And if you guys, I think Chad has got contact information if you want to get a hold of him directly. And with that, Jerry, I'll throw the floor back to you.
All right, sounds good. Again, thank you from me to Chad, as well as you, Kurt, for kind of making this, I think, a really interesting webinar. Again, thank you to the DSUA sponsors for their continued support, and, and a big thank you to all the board members that, I mean, you see myself and you see Kurt, but Travis Reynolds from GE, as well as Sean Vernick from RPM, Craig Henry of AEP, Dave Kahn of Gecko, and Wes Painter of Eastman. So everyone's kind of, had their fingers and some input on this. So a big thank you to everyone, since everyone's kind of given their time to help put this together. So we're always interested in feedback. If you guys think of any other questions you guys would like to ask Chad, continue to reach out to us. You can reach out to us going through the website and contact us in that fashion. As far as going forward, stay tuned. Once this recording is complete, we'll get it uploaded to YouTube and get a link out there for everyone who either had to leave early or couldn't make it at this time. So hopefully, if other questions come up, we're always happy to take them. Stay tuned. The next webinar we're going to do is going to be November. The date is still to be determined, but the subject will be, we've kind of been talking technology specific for the first three. The intention of the next one is to not be technology specific. It's more theme specific around performance optimization, and lessons learned around that front. So anything as it correlates to DSI, SDAs, CDS. So we're still interested, looking for speakers. So if anyone is interested in wanting to give a talk during that slot, then reach out to us. And I guess with that, we'll kind of close this out. And again, thank you to everybody, and we'll look forward to catching you sometime in November.
All right. Thank you.
Thanks. Take care, guys.
Take care.